Here's another video on how the derivatives of both algebraic and transcendental functions are used to solve time rate problems. A problem in related rates is one involving rates of change of related variables. In real-world applications involving related rates, the variables have a specific relationship for values of t, where t is the measure of time, and this relationship is usually expressed in the form of an equation which represents a mathematical model of the situation. And to illustrate the techniques on how to solve time rate problems, allow me to give you three simple steps that you might want to follow. Step number one is to find an equation involving the variables which is true for any time t. Number two is to differentiate the equation obtained in step one with respect to the time t. And number three, determine the unknown time rate variable from step number two using the relationship drawn in step number one if needed. And let me just give you an illustration. I have here a problem which involves rectangular parallelepiped. At a certain instant that the dimensions of a rectangular parallelepiped are 4, 5, and 6 feet, and they are each increasing respectively at the rates of 1, 2, and 3 feet per second. At what rate is the volume increasing? Okay, just to illustrate the rectangular parallelepiped, we shall let x to be the width of the rectangular parallelepiped with its corresponding rate of change in width, which is denoted by dx dt. And we shall let y to be the length and z to be the height, with corresponding dy dt to be the rate of change in length with respect to the time t, and dz dt is the rate of change in altitude or height with respect to the time t. And we shall recall that the volume of a rectangular parallelepiped is length times width times height, which is equal to xyz. So we shall differentiate this equation, and this will serve as our working equation with respect to the time t. So we have dv dt equals derivative of xyz in terms of derivative of x in terms of t. So we have yz dx dt plus we shall now differentiate y in terms of t. So that's xz dy dt plus we shall do it in z. So we differentiate z with respect to the time t. Just copy xy since this is constant, and differentiating z with respect to the time t is dz dt. So at a certain instant that the width is equal to 4 feet, that the length is 5 feet, and that the altitude is 6 feet, the rate of change of width with respect to the time t is 1 foot per second, dy dt is 2 feet per second, and dc dt equals 3 feet per second. By direct substitution to this formula, we shall have dv dt equals 5, that's y, times 6, that's z, times dx dt, that's 1, plus 4, that is your x, times 6, that's z, times 2, that is your dy dt, plus 4 is your x, times 5, which is your y, times 3, which is your dz dt. And solving this equation, dv dt is equal to 138 cubic feet per second. So therefore, in conclusion, in a certain instant that the dimension of rectangular parallelepiped is 4, 5, and 6 feet respectively, and each dimension is increasing at a rate of 1, 2, and 3 feet per second, then the volume is increasing at a rate of 138 cubic feet per second. Another example. A ladder 25 feet tall is leaning against a vertical wall. The foot of the ladder is pulled horizontally away from the wall at a rate of 3 feet per second. How fast is the top of the ladder sliding down the wall when the foot of the ladder is 15 feet away from the wall? So at a certain instance, when you pull the foot of the ladder away from the wall, so there will come to a point that the ladder will look like this. Okay, so, or when you pull it towards the wall, there will come to a point that the ladder will look like this. Okay, and with that, we shall let x to be the distance of the foot of the ladder to the wall, and we shall let y to be the distance of the top of the ladder to the ground with its corresponding rate of change. We shall let dx dt to be the rate of change in x with respect to the time t, and dy dt is the rate of how fast the top of the ladder is sliding up and down the wall. And then by some Pythagorean principle here, we shall notice that 25 squared equals x squared plus y squared. And differentiating, so we have 0 equals 2x dx dt plus differentiating y squared in terms of t, so that's 2y dy dt. And you can reduce this equation as 0, you divide everything by 2, so that's x dx dt plus y dy dt. And at a certain instant, that dx dt is equal to 3 feet per second, okay, and x is equal to 15 feet, we shall now look for dy dt. Dy dt again is the rate of how fast the top of the ladder is sliding down or sliding up the wall. Okay, so when you observe at the equation, our working equation is 0 equals x dx dt plus y dy dt. And we're looking for dy dt here, and dx dt is 3, and x is 15, so we shall now look for the value of y. At a certain instant, that the foot of the ladder is 15 feet away from the wall, we shall now compute for the value of y. So 25 squared equals 15 squared plus y squared. And it follows that y squared equals 25 squared minus 15 squared, and y is equal to the square root of 625, that's 25 squared, minus 15 squared is 225. And 625 minus 225 is 400, and the square root of 400 is 20. So we have y equals 20 feet. And we shall now replace x by 15, dx dt by 3, and y is 20, and dy dt is what we are looking for. So we shall now have 0 equals 15, that's x, times 3, that is your dx dt, plus 20 dy dt. And solving for dy dt, we shall have dy dt equals 15 times 3 is 45. You throw it on the other side, so that's negative 45 over 20. And we shall have negative 9 over 4 feet per second. So this negative sign indicates that y decreases as the time t increases. And in conclusion, we can now say that the top of the ladder is sliding down the wall at the rate of 9 over 4 feet per second when the bottom of the ladder is 15 feet away from the wall. Problem number 3. Water is flowing at a rate of 2 cubic meter per minute into a water tank in the shape of an inverted cone with an altitude of 16 meter and base radius of 4 meter. When the depth of the water is 5 meter, we shall find for letter A, at what rate is the depth of the water in the tank changing, and letter B, at what rate is the radius of the top of the water in the tank changing. Okay, to illustrate, here is the inverted conical tank, okay, with radius equal to 4 meter and altitude of 16 meter. So the water is being poured into the tank at a rate of 2 cubic meter per minute. So which means the VDT, the rate of how fast the water is flowing into the conical vessel, is 2 cubic meter per minute. And we shall now let R to be the radius of the top of the water and H to be the altitude of the water. Okay, so we let H to be the depth of the water, and R, and with its corresponding dH/dt to be the rate of change of how fast the water is, or the rate of change of the altitude of the water to the conical vessel. And R is the base radius of the water, which with its corresponding rate of change dRdt. And you will observe here that the rate of change of the rate of how fast the water is being poured into the conical vessel is 2 cubic meter per minute. And we shall recall that the volume of a cone is equal to 1/3 pi r squared h. And we shall now differentiate each variable here with respect to the time t. So we have dv dt equals differentiating r with respect to t. So we have 1/3 pi h, that's constant, and then the derivative of r square is 2r dr dt. So that's why we have here 2/3 pi r h dr dt. Plus, we shall now do it again with respect, we shall now differentiate h with respect to the time t. So we have 1/3 pi r square dh dt. And then at a certain instant, that the volume, that dv dt is equal to 2, and that the height of the water is equal to 5, okay? So we shall now use these quantities to substitute to our working equation. However, we only have dv dt, we have h, okay? But we do not have dr dt and r on this specific situation. Alright, so what are we going to do now is to look for the value of r and dr dt so that we can now have our dh dt. To do so, by similar solid, we can now observe this relationship between h and r, that 16/4 is equal to h over r. And this follows that r is equal to 1/4 h. Okay, so we have r times 16, so that 16r equals 4h, and then we divide everything by 16, so we have r equals 4/16h, and that will give us 1/4 h. And then differentiating r with respect to t, we have dr dt, and then differentiating h with respect to t, we have 1/4 dh dt. So we shall now have dr dt equals 1/4 dh dt. And we shall now look for the value of r whenever h is equal to 5. So we have r equals 1/4h, and when h is equal to 5 at a certain instant, so we have r equals 1/4 times 5. So we have r equals 5/4 meters. Okay, and then I think we are all set. So we have dv dt equals 2, okay, and then 2/3 pi, r is 5/4 times h, which is 5, and then dr dt is 1/4 dh dt, plus 1/3 pi, then r is 5/4 square, then dh dt. So we have 2 equals 2/3 times 5/4. So again, I guess this is 5 times 5, that's 25, times 2, that's 50 over, this is 4 times 4, that's 16, times 3, that's 48 pi dh dt. And then we have plus 5 squared, that's 25. And then 4 squared, that's 16, times 3, we have 48, okay, pi dh dt. And then we have 2 equals, combining these two, we have 75 pi over 48 dh dt. And then we can now say that dh dt equals 2 times 48 all over 75 pi. Okay? And then we shall now have dh dt equals 32/25 pi. So 75, we divide this by, we shall now divide this by 3. So this is 16, and this will become 25, and 2 times 16, that's 32/25 pi. So this is the rate of change of the altitude of the water with respect to the time t. For letter B, we are asked to find the rate of how fast the radius of the water, of the top of the water, is changing. By using this principle, we now have dr dt equals 1/4 times dh dt, wherein dh dt is 32/25 pi, and 32 divided by 4, that is 8/25 pi. So this is our dh dt. That dr dt, sorry, that's the rate of the change in the radius of the water with respect to the time t. That's 8/25 pi. Problem number 4. Two cars, one going due east at the rate of 90 km per hour and the other car going due south at the rate of 60 km per hour, are traveling toward the intersection of two roads. At what rate are the cars approaching each other at an instant when the first car is 0.2 km and the second car is 0.15 kilometer from the intersection. To illustrate, let us assume that this is the intersection of the two roads. Okay, and the first car is traveling due east at the rate of 90 kilometer per hour, and the second car is traveling due south at a rate of 60 kilometer per hour. So the two cars are traveling toward the intersection. So there will come to a point that the distance between the two cars will, that the first car will be somewhere here at this point, and the second car will be somewhere here at this point. Okay, and we shall now let x to be the distance of the first car to the intersection, and y to be the distance of the second car to the intersection, and we shall now let z to be the distance of the two cars as they approach the intersection. Okay, and this has a corresponding rate of change. We see that dx dt, that's the rate of how fast the first car is approaching the intersection, that's 90 kilometer per hour. And then the rate of how fast the second car is approaching the intersection is 60 kilometer per hour. And we shall now let dz dt, okay, to be the rate of how fast the two cars are approaching with each other. So by Pythagorean principle, we can now see that z squared equals x squared plus y squared. And then differentiating all this variable with respect to the time t, we shall now have 2z dz dt plus 2x dx dt plus 2y dy dt. And you can observe that each term contains 2. So we can now reduce this of the form z dz dt equals x dx dt plus y dy dt. And at a certain instant, that the first car is 0.2 kilometer away from the intersection, and that the second car is 0.15 kilometer away from the intersection, we shall now be looking for the rate of how fast these two cars are approaching each other. Okay, so at a certain instant, we shall now look for the value of z. As you can notice in our working equation, we have z dz dt equals x dx dt plus y dy dt. So we already have our dx dt, we already have our dy dt, we now have our x and y, and we shall now look for dz dt, but we do not have this value of z. Okay, by Pythagorean principle, we shall now have z squared equals x squared, that's 0.2 square, plus y squared, that is 0.15 square. And simplifying this, we shall have z equals the square root of 0.2 square plus 0.15 square, which is equal to 0.25 kilometers. So at a certain instant that the first car is 0.2 kilometer away from the intersection, and that the second car is 0.15 kilometer away from the intersection, then the two cars are 0.25 kilometer away from each other. And then substituting these quantities to our working equation, we shall have z, that's 0.25 times dz dt equals 0.2 times negative 90. I affix the minus sign here because, as you can observe, as the first car approaches the intersection, their distance decreases, and therefore the rate of how fast the car approaches the intersection will be negative. Same with dy dt, which is equal to 60 kilometer per hour. We shall affix the minus sign since this car is going due south and its distance gets smaller and smaller as it approaches the intersection. So we shall have 0.25 dc dt equals 0.2 times negative 90 plus 0.15, that is our y, times dy dt, which will become negative 60. And as you can notice, as these two cars approaches the intersection, their distance will decrease at a certain point, that the second car is located somewhere here, that the first car is located somewhere here, then their distance gets smaller. That's why we have negative here, and negative 60. And then looking for dz dt, we shall have 0.2 times negative 90 plus 0.15 times negative 60 divided by 0.25. And executing this on your calculator, we shall have dc dt equals negative 108. And this negative indicates that the distance between the two cars gets smaller and smaller as they approach the intersection. So in conclusion, the two cars are approaching each other toward the intersection at a rate of 108 kilometer per hour. And last problem. An airplane is flying west at 500 feet per second at an altitude of 4,000 feet, and a searchlight on the ground lies directly under the path of the plane. If the light is kept on the plane, how fast is the searchlight revolving when the airline distance of the plane from the searchlight is 2,000 feet due east? Okay, to illustrate, there is a plane which is 4,000 feet from the ground, and under the path of the plane, there is a searchlight which follows the airplane. And we shall let the time t to be the time that has elapsed since the searchlight spotted the plane, and x to be the distance of the plane due east from the searchlight, and and theta, we have an angle theta to be the angle of elevation of the plane at the searchlight. Okay. And as you can notice here, we can now have our dx dt, which is equal to 500 feet per second. And do not forget that the airplane is flying west. That means to the left. Okay, so we shall now affix the minus sign. Okay, and d theta dt is what we are looking for whenever x is 2,000 feet. Whenever the distance of the airplane to the searchlight is 200 feet. So again, by the Sokatoe principle, since we can now observe a right triangle here, we now have tangent theta equals 4,000 over x. And then differentiating this, we have secant squared theta d theta dt equals negative 4,000 over x squared dx dt. That's the derivative of 4,000 over x in terms of t. Okay, and then therefore, we can now say that d theta dt equals negative 4,000 over x squared secant squared theta dx dt. D theta dt again is the rate of how fast the searchlight is revolving when the airline distance of the plane from the searchlight is 2,000 feet due east. Okay, to do this, we shall now have to look for the value of secant squared theta at an instant wherein x is 2,000 feet. And again, by using this principle, tangent theta equals 4,000 over x, we can now see that when you replace x by 2,000, we have tangent theta equals 4,000 over 2,000, which is equal to 2. And then you recall that secant squared theta equals 1 plus tangent squared theta. And we shall now have secant squared theta equals 1 plus, you replace tangent theta by 2. So we have 2 square, that's your tangent squared theta. And it follows that secant squared theta equals 5. So we shall now look for d theta dt whenever x is 2,000, whenever secant squared theta is 5, and that dx dt is negative 500. So d theta dt equals negative 4,000 all over 2,000 squared times 5 times negative 500. And executing this on your calculator, you will obtain 1 over 10 rad per second. And this is the rate of how fast the searchlight is revolving when the airline distance of the plane from the searchlight is 2,000 feet due east.